Hello, everyone. My name is Ronaldo Murillo Nolasco, and I am the lead instructor of the Autonomous Cognitive Assistant course, aka CogWorks. In this class, we introduce students to cutting-edge machine learning technology, where on each week we focus on a different modality. On week 1, we focus on audio. In week 2, we focus on images. And on week 3, natural language. Our goal of the course is to develop deep non-black box understanding of machine learning concepts by building everything from scratch, underpinning the mathematical formulations that give rise to these technologies. For example, in week 1, we developed our very own song recognition application using signal processing concepts. By the end of week 2, students develop a photo sorting application that sorts photos by subjects' faces, leveraging their understanding of convolutional neural networks. And in week 3, we use word embeddings and neural networks to develop a semantic image search application. And to top it all off, in week 4, students use everything they've learned in the class to create their very own cognitive assistant technology. In this class, students get to use their understanding of mathematics and programming skills in Python to create powerful technologies. Lovely. Okay, so that was my assistant Reynaldo, lovely, presenting the course very well. What we're going to do now is demonstrate the projects from each of the 5 teams in this course. So we're going to transition to our first team, that is Team Troubleshooters, Team 1.
Hello, everyone. We are the team Troubleshooters, and this is our final project, text detection. This is our agenda for today, how our slides are formatted. And this is our team.
I'm a Brewer.
I'm Ansh.
I'm Evan.
I'm Michelle.
I'm Minjay.
I'm Satvika.
And our TA is Maggie, and our instructor is Reynaldo.
So what's the problem? We've all been there, staring at lengthy textbooks, dense reports, or complex documents that take hours to read through. Just look at the student's review. Content that's overly complicated when it could be explained simpler. In today's fast-paced world, we need a way to quickly extract key insights from lengthy documents without losing important information. That's the problem we're solving. Next slide. Our solution is a 3-step process that transforms images of text into summaries. First, we create a web-based interface where users can simply upload an image of any text, whether it's handwritten notes or printed documents. Second, we implement our own OCR model, that's optical character recognition, which essentially means teaching a computer to read an image and convert it into actual text that can be processed. Finally, we use a large language model to automatically generate concise summaries of that extracted text. So in just a few clicks, you can go from a photo of dense material to a summary.
So the idea is that first, a user will upload an image of some text that they want summarized. Next, it is split into individual words and pre-processed. Then each word clip is fed into the model, which predicts what each word is. And then finally, the words are all concatenated and passed into the Gemini API, which generates a summary.
The first approach we took to designing this model was a simple classification model in the form of a deep learning convolutional neural network. We trained on 171,000 images taken from Kaggle datasets of printed and handwritten characters, and we made the model with 3 convolutional layers and then 3 dense layers, and then we eventually added another layer for dropout to combat overfitting. The model was supposed to take in single characters as input, and these would be segmented from the larger input image using OpenCV. And the output to be predicted as one of 62 classes, including 10 digits, all the letters uppercase and lowercase. However, the reason we couldn't continue with this design was that even though it trained to 92% accuracy on training and validation data, it was not viable because the predictions on new input images that we gave it were completely inaccurate. This was mainly because of the segmenting that we used. OpenCV was not able to handle really big images, and it cut the characters too close compared to the images we've been given in the training and validation data. Basically, they were too clean. An example of this, we gave an input image of the word non-specialists, and even though it identified the characters correctly, the output that the model generated was complete rubbish, although it did get a couple of the S's correct.
So what's the fix? In our first iteration, we used a CNN trained on individual characters. So CNNs or convolutional neural networks are good at recognizing patterns and visual data, but they struggle a lot when you give them the varied inputs we need our model for. We can utilize a RNN or a recurrent neural network on top of our CNN layers, which weights the character predictions based on the characters before. This way we can take advantage of the sequential nature of characters and words. Like Savika mentioned before, an issue we had with a simple OCR was that the data was too clean, which made accuracy really, really poor when input wasn't perfect. Method we used to try and fix this was data augmentation, which is when we slightly distort and transform the data before feeding into the model, which makes it more closely match our usage scenario. So this is our final model architecture. The kind of OCR architecture that takes advantage of RNNs is called CRNN, which generally has three main parts. We use ResNet 18 as our CNN, which is a versatile convolutional network to get descriptor vectors of the images. The sort of meta RNN choice is bidirectional LSTM, or long short-term memory for OCR, which is especially good at avoiding the vanishing gradient problem. Loss is how we score the outputs from the model. We give every output a loss score based on how far away it is from the truth value. The two data sets we trained the model on came from Kaggle. The first one is MNIST, the MNIST dataset for synthetic or printed word images, and the GoodNotes GNHK dataset for handwritten text. Training the model was really slow and computationally expensive, and we couldn't do it on our own machines. So we went to cloud computing. We used Google Colab to connect to their GPUs. So we could use hardware acceleration via PyTorch and their tensors. After about 70 epochs, we reached a final validation accuracy of 86%. We didn't have a lot of time to make it better and experiment more because of time constraint. We only had a few days.
We're now going to be moving on to our demo of the final project. So as we can see, we built a small little UI. And when we upload an image, for example, this is going to be an image of some handwritten notes. As you can see, it is bullet pointed. And if we wait a second here, the model reads all this text and generates a summary for us. Now, if you look carefully, you can see that this text is about recursive algorithms, a rubric, and some details, right? If we look into the summary in specific, we get certain words like recursive algorithms, which shows that the model works well and accurately. This works similarly for non-handwritten data as well. If we look at this picture of a portion of a book, even though the image is not perfect, you can see that this little edge is bent upwards and the book has different lighting on both ends. The model still works well. As we can see, this portion is about physics, Nobel Prizes, experiments. We can see that things like the Big Bang Theory and cosmic microwaves are included in the summary, which shows the model's accuracy. Now moving back to the presentation. This is our experimentation results. As we stated before, the CRNN had an accuracy of 86%, while the classification model had an accuracy of 92%. We chose the CRNN, again, because the classification model was quite inaccurate when it came to other types of data. One thing to note is that our model was bottlenecked by the usage of OpenCV, which tended to be quite inaccurate when it came to handwriting data, although it was quite good at printed data, as we can see here.
All right, so there are many key takeaways to have from this project, and first of all, we went on Google Docs and brainstormed and wrote out tasks for each other. We delegated tasks and split up into separate groups to complete each task. Some task examples are pre-processing, CRNN building, and model training. For the research we did, we researched how a CRNN works and how to build it, and we worked with multiple data sets from Kaggle. We also had to learn how to lower training time, and we came across we tried to create a user interface using Streamlit. As for testing, we used many normalization preprocessing techniques on the data set, and we used jittering data so that like the data is not too clean. And we used Google Colab to accelerate our model training and store parameters. And we used regularization to prevent overfitting.
Thank you. That was our presentation.
Just a moment. We're going to relinquish the screen share. All right. Good job, team. Troubleshooters. Round of applause for them. They did a great job putting that together. It was quite a complex project. Right now, we're going to transition to our Q&A portion for Team Troubleshooters. Hopefully, the audience is as eager as I am to see to hear what the audience has to say.
Good job, troubleshooters. Starting off with question 1, we have a question that asks, how did you all choose which data sets to use?
I can take this question if no one else wants it. So the way we decided our data sets, I mean, obviously, first of all, when we were looking for them, we went through a huge variety of different data sets, printed, handwritten, labeled, unlabeled, trying to figure out what we wanted to do with this project, since after all, choosing the data set was one of the first steps we took in creating this model. And eventually we came up with this conclusion that we wanted label data of both kinds in order to better model variety and make sure that this is more of a general product than something very specific. So in the end, we decided to choose just 2 data sets, one printed and one handwritten, both labeled.
Great answer. Building from that, how do you use the data sets to help you train the model? And how did you decide which model to use?
I can answer this one. So for the first model architecture that I talked about, involving a CNN without the RNN structure, we used data sets of just characters with their labels, but the second data set involved using labeled words. And each model was specified to work with those specific kinds of data so that the predictions would make sense. So in the case of the first model, it would predict single characters one at a time, and then the second model would predict entire words at a time. And the second model turned out to be more viable because of the robustness of the data and how similar it was to the inputs the user was giving.
Okay, awesome. Moving on to the next question. Let's do, why did you decide to train your own model?
I can take this one. This course is about machine learning, as we know, and there are tools that exist already to do the task we set out to do, I'm sure. But it was a really great challenge, and learning learning the practical challenges that come with training a model was really formative, and then I think our skills all grew a lot through this experience.
Excellent. Seems like we're at time. Good job, Team Troubleshooters, and great answers to the questions.
Yes. Good job, guys. Another round of applause. Good work. Okay, so we're going to head over to our next great team. That is Team 2, Boba Lovers.
This is our final project called Emote IQ, which is a system that could perceive human emotions based on video, text, and audio inputs. Okay, so for our table of contents, we'll start with the team and then move to the problem, solution, objectives, resources, demo, and then takeaways. And then for the team, we have me.
I'm Abib.
I'm Mokshit.
I'm Cynthia.
I'm Pratyush.
I'm Rianne.
I'm Siri.
And I'm Bella, the TA.
Now on to the problem statement. In the modern day and age, understanding human emotion is a critical real-world skill. As you may know, however, emotional tone is often ambiguous and hard to interpret. In fact, 1 in 10 individuals experience conditions like alexithymia, characterized by a difficulty identifying emotional cues. While sentiment analysis tools are present, most are limited. They're often built just for one type of input, like text, and struggle to adapt to more complex or multimodal data, like facial expressions or voice. That's why our team set out to build something more flexible, a system that can understand emotion from multiple types of input and give a more accurate and complete picture of what someone is really feeling.
So our presented solution is to take in 3 modalities. First is visual analysis, where we create a model that continuously tracks human emotions on the face. Second is language analysis, where we create a model that takes text and returns the most probable tone expressed in the text. And lastly is audio analysis, where we create a model that takes in the audio file and outputs the most dominant emotion based on the extracted features.
Our first modality is Emote IQ's Mood Cam. The Mood Cam is a project that uses facial expression model, FER, to correctly identify a person's mood from the camera.
For our project architecture, we used an input camera such as the webcam, and then using that camera, we plugged it into OpenCV. We then did facial expression analysis, and with each detected face, it is analyzed for expressions using the FER library, which returns emotion labels. Then, the system draws bounding boxes and emotion labels onto each detected face in real time using OpenCV. And then this process is repeated for video feedback and being continuously updated, allowing for live facial expression recognition with minimal lag.
Our next part for the modality is talking about FER's model details. So it begins with a face detection system, which identifies and isolates faces present in each video frame. Using advanced detectors, we used MT-CNN. And then it extracts features from those faces. The model pinpoints the key facial landmarks, such as eyes, eyebrows, the mouth, and nose. It then will analyze that shape, the shapes, positions, and textures using CNNs to extract facial features, which are then using emotional classification to classify each potential emotion. The most highly likely emotion is then put in a box in the output, as seen in the example output.
Next up, we have Emote IQ's Text to Feel, and this is a project that helps users determine the most probable tone expressed in a written text.
Now let's walk through how the system's built and how it works behind the scenes. We start with the input. Users type in a sentence or phrase, which is then tokenized and embedded using glove vectors. For our data pipeline, we use the CMU Mosaic dataset, a widely respected dataset for multimodal sentiment and emotional analysis. We manually split the data into 80% training, 10% validation, and 10% test sets. Each utterance was cleaned, tokenized, embedded, and padded to prepare it for the model. As for the model architecture, we designed a two-layer bidirectional LSTM that feeds into a linear output layer, with dropouts to combat overfitting. This allows the model to understand context from both past and future tokens when predicting emotional scores. During training, we use smooth L1 loss, a learning rate of 0.001, and a very small weight decay of 10 to the -5 to reduce overfitting while preserving learning. Finally, the output is an array of 6 emotion scores, one for happiness, sadness, fear, disgust, anger, and surprise. The model gives a score between 0 and 3 for each emotion, and we return the most probable value to help users interpret the most dominant emotion clearly. Our model was able to achieve a remarkable roughly 9% error, which it was able to generalize to the unseen validation and test data as well.
Okay, so that was a lot of text. So here is a visual representation of what exactly we went through. So it takes your user input and then tokenized embeds it. Then we have on the left side how the model was trained, and then on the right you can see what the user eventually gets as the output, which is the most probable emotion. And to the lower left you can see what the interface looks like. So you put in some input text and you eventually get your predicted emotion. And here's our third modality, vibe.wave, where we classify human emotions directly from speech recordings.
For the project architecture, we start by taking a microphone input and then processing that as a .wave file. Then the raw audio is passed through a convolutional encoder, which splits it into 20 millisecond frames and extracts dense feature vectors. These vectors are processed by a transformer network, which models long-range dependencies like tone, pitch, and rhythm. To train without labels, some features or vectors are masked, and the models predict them using surrounding context. A quantization model converts unmasked features into discrete targets using Gumball softmax, serving as prediction references. The model is trained with constructive loss, aligning predictions with correct targets while pushing away distractors. Then after pre-training, the encoder and transformer are fine-tuned on emotion recognition using labeled and audio data. And then from there, we get our final prediction for the emotion.
Okay, for the model metrics, when training, we change some hyperparameters, specifically epochs, batch size, learning rate, weight decay, and save total limit. And those are the values we change them to. After training, we got a test, or after running the model, we got a test accuracy of 87%. And then to the right, there are two graphs that graph learning rate and loss as the model runs. And then as you can see, the values go down as as the model trains. The final loss was 0.01. The benefits of using the pre-trained model was that it had good documentation for the RavDes dataset that we used. It can train directly from raw audio files if they're in .wave format, and the transformer structure helped retain long-range dependencies.
And now we have a live demonstration of our interface and program itself. So here is our whole project. We have 3 different tabs, one for vision, one for text, and one for sound. Here for the vision, I can click to access the webcam and I can see myself through webcam. If I press record, something will show up here and it will show me that right now I have a neutral face. But if I were to smile like this, it shows that I am happy. And let's say I was surprised, so I had my mouth open. It shows that I was surprised. And then if we move on to text, let's say I wanted to have the text, I hate my job. Like this. And I submit it. The predicted emotion, it would say, is sad. And if we put something more complex, like I don't like going to school, I don't like doing my homework, so multiple sentences, and I press submit, it also shows a predicted emotion of sad. And if I move on to sound, there are two different options for sound. You can drop an audio here or click to upload. Let's say I wanted to upload something. I have a little demo file here, and it's going to be just
Really excited to be working with you all today.
You can tell it's like some sort of a happy tone. And if I press submit, it gives a predicted emotion of happy.
Okay, so what were the key takeaways, or in other words, what did we learn from this project? So the three main things we learned were number one, planning, teamwork, and helpful tools. So throughout this entire project, we really prioritized planning and organization, which allowed us to have a good timeline, so we were able to complete our tasks on time. In addition to this, we became a better team and learned collaboration skills, which allowed us to develop things more efficiently. And finally, we utilized helpful tools like VS Live and Google Colab, along with other pre-trained models, which enhanced our workflow and allowed us to complete tasks quicker.
So for our future work, one of the main things we could start with is by enhancing accuracy. We can do this by training on diverse real-world data sets, as well as including more natural speech, complex emotions, and some spontaneous expressions. We can also improve the real-time performance in order to make the system faster and more responsive for live use. And then also we can adapt the model. This can be for Google Meet or messaging platforms or even a potential application assistant. Or we could also improve the usability by adapting the model and make it mobile or for wearable platforms such as Ray-Ban's Meta glasses.
Thank you for listening.
Okay, we're just gonna relinquish the screen share and yeah, let's clap it up for our team, Boba Lovers. Good job, team. All right, so now we're going to transition into our Q&A portion. We had some activity from the audience. It looks like we have a couple questions. Let's start with the first one I see here. One says, this project seems pretty advanced. What was the most challenging part? I'll hand it over to anyone that can take that.
I can take this one. So this is definitely a great question, and I think the best way to address this is to have one representative from each of the modalities talk about it. So since I worked in the text modality, I'll talk about specifically. So from the point of view of text, the most challenging part was working with the CMU Mosaic dataset. While the dataset was definitely, well replicated and it had a lot of invaluable data across all the modalities, it was a little bit outdated, and the documentation associated with it was a little bit ambiguous. So it was definitely hard importing, pulling data from it, and kind of working with it. So in the future, we might look into maybe finding another source of a data set to use.
This is Upyut, and I'm gonna answer for the visual modality. So for visual, I think one of our biggest struggles was incorporating a model to fit the data we were using. Initially, we tried using different pre-trained models. One to note we used was FaceNet, but we realized the model wasn't accurate enough even after we fine-tuned it on a Kaggle emotion dataset. So we tried a different model called the facial expression recognition, or FER, and then we decided to train that on the Kaggle dataset as well to fine-tune it, and we found that we got max accuracy that way.
My name is Akshit, and I'm the representative from the audio group. And one key problem that we ran into was with the dataset, like Pratyush mentioned earlier. We were also using the CMU Mosaic dataset, and because it was outdated and the documentation wasn't great, it was hard to train a model based on that data. And another issue that we had with that dataset is that we weren't able to download the specific audio files from the dataset. And so we switched to the RAVDES dataset, which had good variety in the audio, and we were able to train directly from the audio files.
All right, great job, team. That was a very complete answer. I think we have a fun one from the audience. And I think you guys partially answered one of these, but let's say, what inspired the idea of the project?
All right,
Oh, sorry. Do you want to take
go
that
ahead.
one?
No, go ahead.
Okay. So the reason that we started this project was because over the past 3 weeks, we learned about the three different modalities, and each of us were really interested in different ones. So we decided that we wanted a project that can encapsulate all three of them. And we thought that a tone detection system or a sentiment analysis tool would be the best way to go about it.
All right, yeah, I think that's great. You guys thought we're very thoughtful in this one, and we have time for one more question. Um, Given more time, what features would you like to add?
I can answer this one. So given more time, we'd start to want to have a more sophisticated interface that may be applicable to multiple different other platforms. And also our text, the interface was also a little buggy, so we'd want to kind of optimize that. And then maybe also having the ability to analyze all three components at once rather than having to click to each different modality to use it. And maybe another thing we could do is try to detect more subtle emotions. Right now we have very like uh, broad emotions, maybe like sarcasm or something is what would be a next step of ours.
I see. All right, that's very good. And I'm going to put this one for fun because it came through. Someone from the audience says, "Wow, this project is so cool. How did y'all work through collaborating online?"
Oh, I
Yeah,
can
so
take this one. Oh, no. Oh, go ahead, Rian.
yeah, so to collaborate online, what we did is we split our subgroups into different Discord channels. So we used the voice channels to communicate with one another. And then to make sure all our code fit together, we used GitHub, and then we uploaded and committed changes based on our code. And then once we did that, we compiled all the code into one single code like document, and then we just ran it off there.
All right, good work, team. We worked very hard to put this together. All right, so we're at time, a little bit over. So we're going to head over to our next team. That's Team 3, Get Good.
Hi everyone, this is Team Get Good from CogWorks. Today we're going to present to you our project Lock In. Let's have the team introduce ourselves.
I'm the TA, Steven.
I'm Sophie.
I'm Arimon.
I'm Amanda.
I'm Versag.
I'm Gwyneth.
I'm Kritik.
I'm Lily. So today we'll be covering our project overview, solution overview, a demo of Lock In, and we'll end with results and takeaways of this project.
So let's jump into the project overview then. First, let's talk about the problem. Especially after the COVID-19 pandemic, we've all experienced the struggles of remote work somehow. Sitting through long meetings and classes, ending with sore backs or feeling drained without knowing why. And it turns out that we're not alone. Around 70% of people experience musculoskeletal pain from bad posture during remote work, and over 40% of remote workers report increased feelings of stress or anxiety during remote meetings. And not only are these comfort issues, They're killers of productivity as well because physical discomfort reduces focus and emotional stress makes it harder to think clearly, engage confidently, and collaborate effectively. And without feedback, these issues can go unchecked for hours. So how can we solve this?
Introducing lock-in. This is our solution to the problem. Lock-in is a next-generation Zoom bot helper that is able to analyze the emotions and posture of participants in the meeting. It is able to analyze this and propose suggestions in real time by sending DMs through the chat.
Our project consists of three main components: the posture analyzer, the emotion identifier, and the Zoom bot. Together, these components work together to monitor posture, detect emotions, and provide real-time feedback during virtual meetings.
Next, this is how our project works. So once the recall API joins our meeting, it takes both the transcript and real-time video data of the Zoom meeting. Using the video data, we then classify posture recognition and we then perform posture recognition and emotion detection for each person. Additionally, we gather the transcript and using the timestamps from the transcript as well as the poses or emotions it detected, the LLM, or we use Gemini AI, is able to kind of figure out, hey, maybe this person was sad at this time because they were talking about calculus. So maybe that means that they were having difficulties understanding calculus. And then it sends a direct message to the person through Zoom.
First, we developed the posture analyzer, which monitors sitting positions in real time to detect poor posture. We utilize Google's MediaPipe framework, specifically the pose module. MediaPipe uses deep learning models, specifically CNNs, to detect key human body landmarks directly from video input. CNNs are great at capturing spatial features and images, and MediaPipe builds on that by offering landmark detection, giving us access to 2D coordinates of 33 different body joints, including the shoulders and mouth, which were essential for our posture metrics. In our system, every frame captured in the meeting is first passed through MediaPipe's pose estimation pipeline. From there, we extract just the landmarks we need, specifically the left and right shoulders and the midpoint between the corners of the mouth, and are able to use it later on.
Once we extracted the landmark coordinates from MediaPipe, we fed them into our processing functions, which is where we do the actual analysis, and we designed two primary metrics that our system monitors. So first, the shoulder tilt, where we calculate the angle between the shoulders using a custom utility function. And then if someone is sitting upright in an ideal position, the shoulder line would be close to the horizontal, so any significant tilt beyond the optimal threshold that we found would be flagged. And then next, the mouth to shoulder distance. For this, we take the midpoint of the detected shoulders and measure how far the detected mouth midpoint is. And this gives us a proxy for head forward or slouch posture, since if the mouth is too close to the shoulder line, the person would likely be leaning forward. And then to account for people of different sizes and different camera setups, we use a normalized ratio. And then these two indicators are analyzed independently and ultimately combined. And so if both metrics are bad, we would raise a major posture alert. And then if only one is off, we would offer more specific feedback, either about slouching or shoulder alignment to the user.
So after the system detects landmarks, our system classifies the posture into key statuses. The key statuses we track are good posture, tilted shoulders, slouching, and both. But besides just labeling posture, we added temporal logic. Because posture naturally fluctuates, sometimes someone might just be stretching for a second, and we don't want to send a message every millisecond that the posture changes, since that would just be annoying and inaccurate. So instead, we built a system so that when a posture status changes, like going from good to bad, we don't instantly notify the user. And instead, like we set a timer, and if they are consistently in that position for 10 seconds, only then do we change and consider sending a message. We also have an ultimate warning message if there's bad posture for over 2 minutes, just to give that extra nudge.
Next is the emotion identifier. For the emotion identifier, we use HAR Cascade, which is a classifier that uses HAR features or edges between regions with light and dark, or lines that are vertical and horizontal in order to detect objects like faces. The Cascade classifier takes in the images and then goes through a series of stages where the early stages use simple features to quickly eliminate non-face regions, and the late stages apply more complex features in order to detect the faces.
To actually detect the emotions, we use DeepFace, which is a deep learning convolutional neural network to detect facial features and to get facial attributes such as age, gender, emotion, and race. For our app, we used emotion detection to output a response that then calls an API to Gemini to generate a response that is tailored for that specific emotion. We'll go more in depth about this in the later slides.
This is our bot integration. So in our front end, we use something called a Flask app, and when we run our code, we can subscribe to different event subscriptions. These can include mixed audio, transcripts, video, and audio data. And specifically for lock-in, we mainly focus on the full transcript data and the video separate data. And this can be used, this will be fed into our backend, and these create arrays. And to trigger a message, there must be like a consecutive number of bad emotions or bad posture warnings after feeding those into our ML models. And then once one of the events is triggered as either bad, this is fed into our API, which understands context behind the meeting, and it sends a final message into the Zoom chat. This is a demo of our product. So first we can just call on the Python file. And this should automatically start the Flask app and start the server, and also subscribe to the endpoint using ngrok. And we can see that in our terminal. Now we just put in our meeting URL, we just specify our bot name, and we subscribe to both transcript data and video data, and we gave our WebSocket URL, which just makes sure like all the information is sent to that specific URL. And now this is a demonstration of what happens when the bot's in the meeting. So the bot actually messages Gwyneth, and it understands the context behind the meeting. And in our meeting, we were talking about Fourier transforms, and when Gwyneth was a little bit confused and had a negative emotion, it flagged it and sent her a message.
So now we get to the results. So here, this is just a recap of what it would look like in an actual meeting. And then here are some live use case examples of our application, like using the transcript and context, like what Prasad said before, to actually help participants in an actual meeting. So like in these images, on the model's response on the top left acknowledges Gwyneth's struggle and asks her if she needs help when they're talking about downloading a Git repository in the meeting. And then here on the bottom right, it corrects Sophie's pronunciation when we were talking about discrete Fourier transforms.
Some key takeaways from this project is that we learned about WebSockets, API usage, and pre-trained model use, and we were able to work as a team to research and make a project from scratch. Our next steps would be to implement reinforcement learning, add more features, and add the ability to DM the bot directly. And thank you for listening to our presentation.
All right. Good job, team. Get good. Round of applause for them. Great job. Great job. Okay. All right. We're going to transition over to our Q&A portion. I can see that the audience was submitting questions as they were going. I'll hand it over to their TA to read the questions.
Yeah. So we got a question asking, how do you know what tools to use for this? Did you learn it all from this course, or did you do your own research?
Okay, so I can take this one. So for the 3 parts of our application, we have to do like our own research. to find the CNN models and how to actually integrate Gemini with the Zoom bot to send the messages. But like for the most part, the actual implementation of this was stuff that we learned throughout the course, which helped a lot with this project.
Okay. It's a great answer. Another question was, does this project work for other apps too, like Google Meets or Teams?
I can take this. Yes, it does. So the way we get our video data is through an API called Recall, and that basically we just subscribe to events and we can get different sorts of data types. So, for example, we use the video and transcript data, and the apps available, they include Google Meet, Zoom, Teams, and Slack, and it's pretty wide number of use cases.
Okay, great. Then we had another question asking, it seems to work so well already. Are there any issues it still has or anything that needs to be improved upon?
I can take this one. One challenge currently is that the bot relies more on a ideal camera view. So if the camera angle is off or if the lighting is extremely poor, the detections can get thrown off. For example, if your shoulders are slightly out of the frame, the bot might not be able to calculate the angles or distances that it needs to classify your posture, which would mean it will no longer function as intended. And then another limitation currently is that while it's good at detecting posture and emotion and sending feedback on that, it's not that interactive. So if a user tries to ask the bot for clarification or responds to it in the Zoom chat, it won't understand or reply. So it's just like a one-way communication for now. So yeah, those are two challenges right now that our bot currently faces and that we hope to address in the future.
Yeah. And then I think we have time for one more question. Someone asked, how would reinforcement learning better this project?
I can take this one. So if we were to use reinforcement learning, we would likely use it to better fine-tune our parameters. So for example, in posture detection, we have like the two main aspects of like if your shoulders are tilted and like chin to shoulder distance. And so like everyone has like a different neck height, I guess. So like using reinforcement learning, we could actually see if they're slouching or if it's just like what the computer thinks. And then that way we can make the threshold more accurate. And then in the future, if we make it so there's like a baseline, like a adjusted detection, depending on like what person is the posture detection is being performed on, this reinforcement learning will just help make it a lot more accurate for each individual person.
All right. Wonderful. Team Closed AI, another round of applause for them. They did a great job here. It kind of made me think, okay, they were on Zoom this whole summer. I don't know if they're trying to send me some low-key messages, but there we go. Our next team is going to be Team 4, Closed AI. Hopefully OpenAI is not listening. If they are, listen closely.
Hi everyone, this is our CogWorks final project, Highway I. Our team name is Closed AI, which consists of Emre, myself, Samba, Joshua, Sophia, Lori. Our TA is Priyana and our instructor is Ronaldo. So everyone says the US has no culture, but I disagree with that because we have road trips. However, these road trips can be dangerous and boring. So for our project, we designed solutions for both of these problems. So our first solution is Insomnia, which is a real-time sleep detector that ensures you never fall asleep when behind the wheel. If your eyes are closed for too long or you're dozing off, an alarm will ring. We want to keep the American dream and the driver alive. Second, we have I Spy with My Little AI, which is our take on a classic road trip game. This is perfect for distracting kids in the back seat.
Introducing Insomnia. Every year, around 50,000 people in the United States are injured due to drowsy driving. What's even more alarming is that 21% of fatal crashes are a result of drowsiness while driving. These numbers highlight a serious issue, and we're here to help resolve it. Our system workflow uses eye cropping and a convolutional neural network, which is often used in image recognition, to set off alarms when drivers appear to be dozing. We use MediaPipe face mesh to detect and crop eye regions directly from video frames. For every frame, we locate 4 landmarks around each eye, rotate the frame, and crop out eye images. We trained our PyTorch CNN on the closed eyes in the wild dataset, which includes images of both open and closed eyes captured under real-world conditions. To apply this in real time, we monitor the model's predictions for each frame. If the model detects closed eyes for more than 1 second continuously, the system triggers an alarm sound that the user selects from our soundboard. Once the eyes reopen, the system resets and stops the alarm. This threshold helps distinguish drowsiness from normal blinks, which typically last less than half a second. Here's a visualization of the MediaPipe to CNN pipeline. For each eye, we use the inner and outer corners and the upper and lower eyelids to crop images of eyes. Using the coordinates of the eye corners, the frames are rotated so that the eyes are aligned horizontally. Before being inputted into the model, each eye image is converted to grayscale and resized to 24 by 24 pixels. The CNN then predicts a number from 0 to 1, which represents whether the eyes are open or closed and the confidence.
As for the model training itself, since the inputs were grayscale images with pixel values from 0 up to 255, we had to shrink that range down to 0 to 1 to ensure stable training. After this, we passed them through several convolution and pooling layers. The convolution layers extracted important details from patches of pixels, while the pooling layers simplified and summarized such details. Finally, we used a linear layer followed by a dropout layer that zeroed random neurons to ensure the model didn't memorize the training data, but truly generalized to new data. Since this task was relatively simple, the goal was to balance accuracy and speed, as we are going to run this model in real time at 30 frames per second. 80% of the data was used for training, and we had a binary cross-entropy loss for gradient descent. We used early stopping in this case with a cap of 1,000 epochs, and we stopped training the model as soon as the validation accuracy fell for over 5 epochs. In total, it took around 2 minutes and 30 seconds and 15 epochs to reach 95.87% accuracy on the validation set. Welcome to Insomn AI. This is our user interface created by Gradio.io. As you can see, we have 2 tabs, the camera feed and the soundboard. The camera feed shows the participant's video using the webcam, and the soundboard contains over 25 different custom alarm sounds that you can use to wake yourself up. We have anything from air horns to classical music and to literally anything. Baba Booey. I think I like the last one. I'm going to click here and choose that one to set as alarm. Go back to the camera feed and start the program. So you can imagine if I'm driving and start to nod off. Baba Booey, Baba Booey. I get woken up. Baba Booey, Baba Booey. There you go.
Next, here are some roadblocks we encountered when working on our project. When testing our model, as you can see here in this image, it incorrectly identified Joshua's eyes as closed. So in order to improve the accuracy of the model, we added a feature to normalize the brightness, which helped with images with bad lighting. We also increased the confidence score threshold from 50 to 70%, so the model has to be very certain that the user's eyes are in fact closed. Another challenge was that if the head was tilted, which is common with drowsiness, the model couldn't recognize the eyes properly. To ensure that eye crops remain consistent despite head tilt, we compute the angle between the eye corners and apply a rotation matrix to align the eyes horizontally. We then extract a cropped image of the rotated eye region by using rotated coordinates of the landmarks. If we were given more time and resources, we would focus on 2 key improvements for our future work. Our model may exhibit racial bias due to the limited diversity in the CEW dataset we trained on, and may underperform on individuals with slightly different differently shaped eyes, or varying skin tones. We would prioritize collecting a more demographically diverse dataset to improve fairness and accuracy of insomniae. Also, we only track whether the eyes are opened or closed as our only drowsiness indicator. We would also want to train the model to analyze body language, such as slouching or slumping heads.
Our next project is I Spy with My Little AI. This is our system architecture. First, we allow the user to upload an image to our server. Then we run the You Only Look Once object detection model to extract the bounding boxes, segmentation masks, and names of all the objects in our image. Then we use k-means to batch out the colors in our segmentation mask to get the most common useful color. For data handling, we store the data separately for each session with unique user IDs for each user. This allows us to have multiple users on our application at the same time. When the user enters text, we embed it with All-Mini-LLM L6 version 2. This embeds the text into a 384-dimensional dense vector space, so we can compare it semantically with the names outputted by Yola. If they're similar, we give the user 20 points. If they're different, we subtract 1 point. If the user used the Show Boxes feature, we'll give them 10 points instead. Everything is hosted on a Flask server, and we're using Cloudflare for security.
And now, let's actually demo the thing. And I'm going to pass it off to Past Me to show you what that looks like.
Thanks, Future Me. So I'm going to use this image that we just pulled off of Street View. And you can see that it's uploaded here, and it tells us that it spies with its little AI something slate gray colored, and that's the actual RGB in that text that it sees. So I'm going to guess that's a car, probably. Let's see. Yes! And you can see I just got 20 points from that because it's a 20 points per correct guess. I could spy again on the same image, but instead I'm going to use a different image, and that's going to be this one of my dog. So with this image, it says that it spots something purple-brown, which does look like the color value of my dog, so let's see. But we can also say show boxes to show what it's actually seeing. So I'm going to say dog, and let's see if it's right. Yes! And you can see I got 30 points there because that was a correct guess, but we used the show boxes hint. And of course we can spy again on the same image if we want to. Passing it off back to Future Me.
Thanks, Past Me. So, what were some roadblocks that we faced during this process? First of all, we weren't originally sessionizing the user's information. So if two people were using the website at the same time and one person uploaded an image, the other person would see that image. Or if one person made a guess, the other person would see that guess. And obviously that isn't ideal. So we sessionized everything, and now it works per user. Secondly, the model itself wasn't all that great at first. You can see that it originally misclassifies my dog as a teddy bear, which is super adorable, but not that great for the actual game, because if you guessed dog, it would say that you were wrong, even though you're not. But we upgraded it to the extra large YOLO model, and now it correctly classifies my dog as a dog, and other things as correct too. And then lastly, there were lots of other little small issues, like it would give you an error if it didn't detect anything in the image, and it wasn't deleting old photos if you uploaded new ones, so we were getting tons of images stacking up on the server, but we fixed all of those things, and now it runs way better. As for some limitations and things we might change in the future, I think we would probably rework how the model actually picks an object. So we want variety in the things that it picks, but right now it's truly randomly picking out of all the things it sees. So if there were 50 books in an image and only 3 other things, it's almost always going to pick that book. And that's bad if, let's say, you play this in a room with a bookshelf. And so we would probably make it pick randomly from a set of all of the names rather than truly randomly from all of the things. We also might want to change how it detects color, because right now it's using k-means and then picking the color that's closest to it, but it isn't that good at picking in terms of what we understand as color. So if a potted plant is in the background, for example, those colors become muted, and so it'll call that gray, even though we can clearly tell that that's supposed to be green. So we might want to saturate those colors up or do some other processes to get it better at doing that.
Our first takeaway is communication. We were able to talk freely when we were discussing our projects. We also used Discord channels to communicate within our subgroups. Second, we have planning. Before starting each project, we made sure to clearly plan out all the parts so that we are more efficient when actually merging all of our code together. Third is perseverance. We faced so many obstacles over the past few weeks, but we still continuously try to improve until the very end. Thank you.
All right. Good job, team. Closed AI. Round of applause for them. Good work. Okay. We're going to transition over to our Q&A portion, and I'll hand it over to Prana, their TA, to feed the questions.
Hi, great job, team. We have our first question. Why did you shrink the data, and what makes it train better this way?
I can take this one. So the reason we shrink the data was since we used the closed eyes and the wild dataset on Kaggle, it was only available in grayscale and 24 by 24 pixels. I feel like if we had more time, we would have gone for more diverse datasets that had more color and a larger quality. But due to the time restrictions, we ended up using the CW dataset. And so we had to pre-process our input images to match that dataset, or else the model would not be able to predict on that size.
Great answer. We'll be moving on to our next question. What is a feature that you worked on but ultimately decided against for your project and why?
Yeah, I can take this one. So for Insomnia, we initially planned to use yellow for that eye detection, because it provides a bounding box around the eyes, which would make cropping the images easier. However, we eventually decided against this because there was a lack of annotated data for identifying eyes on faces, especially for closed eyes.
Great answer. All right, we'll be moving on to our next question. How can you make sleep detection more robust?
I could also take this one since I worked on that model. For robustness, the feature like Lori and the others mentioned was adding posture to the mix. So we would use media pipe for body posture and upper body poses, and we could train our model on those to ensure that it doesn't only depend on eyes, which is very haphazard, but we would also incorporate all those other things. Another exciting feature we wished we could do was training the model on its own prediction. So once we predict an image, if the model is over 95% accurate on that image, then we would loop that back into the training data and retrain it so it'll be more accurate for that specific person.
Once again, a great answer. Our next question is drowsiness detection based solely on the subject's eyes, or are there other factors involved? Would it still work if the subject is wearing sunglasses?
Yeah, so Insomnia only should work fine if the user or driver is wearing normal glasses, but issues would arise if the frame is too thick and if there's glare from the sunlight, then the accuracy of our model would be reduced. And as for sunglasses, obviously you can't see the eyes clearly, so we would have to use other indicators such as slouching or nodding heads, as Joshua and Sophia have mentioned.
All right, fantastic. I think we might have time for one last question. Given that the I Spy application is for children, can you make it work by talking instead of texting?
So we were originally planning to make it work with talking as well, but we realized that would be outside of the scope given the time we had. But given more time, we could definitely make it work with a text-to-speech model and a speech-to-text model, and it would be very interesting to implement.
All right. Good job, team. Closed AI. You guys did a great job there. Round of applause for them. All right. So we're concluding QA for there, and we're going to head over to our next team. That is Team 5, Pickle Ball Lovers. Floor is yours.
We're the Pickle Ball Lovers,
And our project is Pickle 5. It stands for Predictive Illegal Dump Site Classification via Knowledge-Driven Learning from Earth Observation. We're going to start by introducing our team, identifying the problem with a solution overview and a quick demo. Then we will describe our results through multiple iterations, our key takeaways, and what work we would do in the future. So this is our team. Our TA is Sarvesh.
I'm Aditya.
I'm Adi. I'm Akansh.
I'm Nandini.
I'm Nitya.
I'm Fasan.
And I'm Vera.
So this is our project objective. To start our project, we identified a real-world problem and an according problem statement. Illegally placed trash zones present a threat to the health of urban communities and the environment. These unmanaged dump sites can contaminate resources like soil and water, degrade air quality, and make diseases much more pervasive. The current solution that people use is that some governments and cities rely on word of mouth or manual classification. However, this can be inconsistent and inaccurate. In accordance with our problem statement, we created our project objective to train a model that can identify areas of illegal dumping, given satellite images, and classify the type of waste on site. This model would make dump site classification much more accurate, consistent, and faster, leading to faster decision making.
Now we have the solution overview. So our idea, like Nandini said, is to allow the government and NGOs to identify these illegal dumping sites through an automated process instead of relying on word of mouth or manual classification. Our solution is to create a classification model that allows users to 1, detect the location of an illegal dump site, 2, identify the type of waste that's in that dump site, and 3, return a confidence score based on how confident it is that it did those past 2 tasks correctly. In order to help us finish this project, we used a couple of resources. First, we have the aerial waste dataset. This was a dataset of over 10,000 aerial images that were classified by different factors, such as where the dump site was, the type of waste in that dump site, and the mode of storage of the dump site. Second, we had the aerial waste model. This was a pre-trained model that we had, where once given an image, it would generate a heat map showcasing where a dump site is most likely located. Third and finally, we had the ResNet 18. This is a residual neural network with 18 layers. It's very good at image classification, and we fine-tuned it for our purposes. So first off, once getting into this project, we needed a way to extract just the dump site from an overall aerial image. In order to do this, we took our data set with all our images in it, and we generated a heat map that corresponded to each image. This way, once we saw based on each heat map, we chose the hottest location in a heat map, and that corresponded to where our dump site would be. Then we drew a 51 by 51 bounding box around that. This allowed us to first know where our dump site was located in the heat map, and 2, extract that dump site for further classification. Then, from the bounding boxes, we would choose a number k, which is the number of bounding boxes in the image that we would choose. A higher k value will give us more bounding boxes as our data. And then from each bounding box, we would also rotate and reflect it to get even more data values. And we would store all these bounding boxes in a pickle file. However, there was a problem with our data. The distribution was very uneven. As you can see in the waste type, rubble, rocks, and bulky waste had way more images than all the other data types. And in waste storage, heaps not delimited and containers had way more images than the other storage methods. So this made it really difficult for us. And in addition, there weren't thousands of images that we could use. The max was like 95 or 65, which isn't that much to train our model. So due to this problem, we had to create multiple bounding boxes in each image and rotate and reflect it several times to really have more images to train our data.
So this is an overview of the pre-trained aerial waste model we used for generating heat maps. So first, it takes in the image from the dataset, and the main model is ResNet 50, trained on ImageNet processes. And from there, the output of that ResNet 50 is normalized. And then we push it through a final classifier, and the heat map is returned. So for our classification model of different waste types, we used an ResNet 18 model. So the main advantages for why we chose ResNet 18 was one, skip connections, which allows layers that aren't next to each other to be connected. This can help prevent problems like gradient decay during our training. Additionally, dropout, which is where we deactivate certain neurons in the network, also helps with generalization, and batch normalization helps stabilize learning as well. So this is a visualization of our pipeline. First, we take an image from the dataset, and then we rotate it and reflect it. And then from there, we generate the heat map. And then we take the K bounding boxes with the highest heat map values, and we return those as cropped images. And then the bottom 4 images are visualizations of the ResNet 18 model at different layers.
We made a website with HTML for a demo. On the website, the user could pick a satellite image of a dump site or input one of their own. The model then returns the classification of the waste, its confidence, and a heat map of the dump site. Since our model is in Python, we set up a backend server with a Flask framework. The API receives the image from the website, runs all of the functions, and returns the information. We trained our model a bunch of times to get better results. We tried only using images with a single waste type, but the accuracy was really low since there was only a few images like that. To increase the amount of data, we included images that had information about its mode of storage, and that increased accuracy a little. We again increased data by rotating and reflecting each image. Finally, we got the best accuracy by reducing the size of the box around the waste, but putting more boxes per image. So we ended up with a final accuracy of 91% after 10 epochs.
Now we're going to go over some key takeaways and some roadblocks we encountered. So the first takeaway was how important communication was with the project this big. We communicated effectively with the use of several applications like GitHub, Google Drive, and Zoom. The second takeaway was how to handle imbalanced data, which is basically real-world data. We worked with the aerial waste dataset, which was pretty imbalanced, like we said before, in terms of several waste categories with few images. So we had to do some pretty unique sampling and unsampling techniques. Now, the third takeaway was how to actually train models and troubleshoot them. Like we said, with the data, our training data sets weren't perfect. So we had to do a lot in terms of troubleshooting our models. And we dealt with issues with our models such as like extreme overfitting and then low accuracy. One of our roadblocks was that with the model, we trained it using CUDA, which allows you to use your GPU instead of CPU and is generally faster. So when we put it on the demo UI site, we couldn't run it with most devices. We could only run it with the device that had CUDA. Another roadblock we encountered was figuring out the best size to crop our images. This was difficult due to some image processing errors, but this is also very important to optimize model performance. Our third roadblock was basically the accuracy of our model. Sometimes it would be too accurate and overfit the training data, which caused high validation set accuracies, but very, very low test accuracies.
Now let's end with our future work. So going forward, here's what we want to do. First, we want to increase the model accuracy on our current number of classes. From there, we can expand the number of waste classes to all the waste types in the dataset. And finally, we can implement more measures for city cleanup and increase greenery, such as a model that can find the optimal location for vegetation growth.
Here are our references. Thank you.
All right, good job, Team Pickleball Lovers. Round of applause for them. All right, they did a wonderful job putting that together. It's an incredibly complex project, and it's wonderful to see the pieces come together. So I'm gonna turn it over to their TA to feed the questions. Sharvesh?
All right. Great work. And yeah, so we have a bunch of questions, and I think the first question is, what is overfitting and how was it an issue with the project?
I can take this one. So overfitting is basically where your model has high training set accuracies, but low testing accuracies. And what's basically happening is that it's tuning its parameters too much to the training and not leaving room for generalization. So it's not going to be as accurate for like real world data, but it is going to be deceptive in that it shows that it's accurate for your training data.
I guess the next question is with specific to a function. So the next question is, how does identify dumps work? I guess this is in reference to a specific function.
I can take this one. So identify dumps takes in the heat map image that's generated by our pre-trained classifier. So that heat map has values between 0 and 1 for how likely a point is to have trash. So what we want to do is find the k points around which we have a high probability of trash. So to do that, we also took in the bounding box size. So we iterated for each point in the image. We took the sum of all heat map values within the surrounding box, and then we found the k points with the highest summed values, and we returned those.
All right, that's a great answer. I guess the next question is a follow-up from the previous question. How does taking k bounding boxes from the image make training any better? Wouldn't more samples from the same image increase overfitting?
I can answer this. So the problem we ran into was we didn't have enough images. So having more bounding boxes, there were like separate bounding boxes in the image. So we didn't like look at the image as a whole. We just took a small crop of the image. So when we could get more crops of the image, we basically had more data to put into our model. And all the crops are different. So none of the crops were overlapping.
All right, so the next question is specific to the website. So the question is, were these web tools taught? How did you decide which tools to use?
I can answer that. So we did initially use Gradio to make our website because we could easily input our model within it, but we found that it was kind of limiting in the kind of aesthetic features we could put in. So instead, we made the website using HTML, and then we created a separate backend server that had all the Python and the model. So then we connected those two using a Flask framework, and then we ran both on local servers.
All right, I guess we have time for a couple more questions. The next question is with respect to the architecture. So what's the difference between ResNet 50 and 18?
I can answer this one too. So basically, ResNet 50 has 50 layers and ResNet 18 has 18 layers. This means that ResNet 50 can detect more complex patterns and have a higher accuracy, so it was well suited for the model that generated the heat map. However, it was too good for the classification and started overfitting the data because it was like looking too closely at the patterns. So we switched over to ResNet 18 so that it didn't memorize the training data and it would work better for our testing data.
All right, I guess we have time for one final question. It looks like your project has multiple functions. How did your team divide the project and work together?
I can take this. So we started by creating a flow chart with all the functions. So we like planned out how would we do this before we started to code. Then when we created a flow chart, we all like took up one function and we assigned it to ourselves to complete. Then after completing the function, the hard part was combining them all together because sometimes the parameters of one function and the outputs don't match up. So we took some time to debug it and compiled them together. And basically, by splitting up the work, we could all like work together and then merge everything at the end. And that worked out for us.
All right, those were great answers. And yeah, Ronaldo can take over.
All right. Great job, Team Pickleball Lovers. Let's give them a round of applause. All right. That's wonderful. Okay. So that was our last team. And that concludes all the demos for them. But I want to take a moment to say that I'm very proud of all the teams and their development this summer. They've done a fantastic job pulling together where they initially did not know each other. And now they've formed a team to accomplish what I consider incredible feats in a remarkable short amount of time. So all of you should be proud of yourselves, and I'm happy to have showcased all of you today. So final round of applause for Team CogWorks for 2025. All right. Thank you everyone in the audience for joining us. Thank you for your questions. Thank you for the enthusiasm surrounding this course. And hopefully you're also able to appreciate the outcomes that we have demonstrated here today. Take care, everyone.